time for us to do some problems involving work and a little bit of force as well. So we get to do physics. Woohoo! Now, before we begin, I just want to put a little disclaimer out there. The last time I took a physics class was a very long time ago. I was actually in high school. I haven't had physics since then. So I don't know any of this newfangled stuff out there. So it's going to be fairly simple and rudimentary. But that's okay. Really, it's just understanding the basics. Once you get the basics, the rest isn't so bad. And to do that, we practice. So make sure you're practicing these problems, not just watching, but doing them. So if you're following along with the video, make use of the pause button. See a problem? Pause it. Work it out. And then if you need help, unpause until I can catch up to you. And then maybe you might continue. All right, pause, keep working. Unpause. And eventually you'll say, aha, I don't even need Steve anymore. That's okay. That's great. You'll love it. It's good stuff. But to get there, we need to start. So let's get to work. Our very first problem. An absent-minded calculus instructor. Absent-minded calculus instructors? Why, I never! Wait, what were we talking about again? Oh yeah, we were doing the problem. Okay. An absent-minded calculus instructor is carrying practice exams 2 floors up to the classroom. I remember back when we had classrooms. They neglect to notice that the exams keep falling out as they go up. Given that the 2 floors correspond to an elevation change of 20 feet, that the initial weight of the practice exams was 10 pounds when starting and 6 pounds when they reached the 2nd floor, and that the exams fell out at an even rate, then use integration to find how much additional work the absent-minded calculus instructor did by carrying the practice exams. Now, of course, what does this mean by additional work? Well, they had to move themselves up. They're not weightless. We're really focusing on you did work moving the exams. How much did the exams make you work? So that's what we mean by the additional work. And, we get to include units. All right. Well, Now, if none of the exams had fallen out, we know that at the start, it was 10 pounds, and they moved 20 feet, 200, and we're done. All right. Well, maybe not quite that easy. So what can we do? Well, let's think about the weight. So we're going to think about the pounds. How heavy were the exams? So we have our picture. We can always draw a picture. In some sense, you have problems like this. If they don't have a picture, you can draw a picture. So we have our stairs here. Okay, and here is our calculus instructor at the bottom getting ready to go up. And they move up. And of course, they'll end up here and at the top. And of course, you don't have to make the picture this detailed, but all along little practice exams all the way up. That fell out. So we think to ourselves, okay, what happened? Well, we know it was a change of 20 feet because it told us 20 feet. That was our first clue. And we can graph what's happening. So really, we should think about things in terms of elevation. So we're going to have our coordinate system be up and down. So we need to make a decision about coordinates. This is going to be a very common theme where we say, where are our coordinates? So let's put 0 at the bottom, and we'll put 20 here at the top, so that we're going from 0 up to 20. Now what we can do is do a quick sketch. And the question is, all right, given that we have here, we'll call this y, where y is where we're currently at. And then, what are we sketching? Well, we're sketching the pounds, which is really saying the force. We know at 0, at the bottom, we know there are 10 pounds. So it's here at 10. And at the time they get to the top, it's 6 pounds. See, it's 6 pounds when they reach the 2nd floor. So that's at 20, and now we're at 6. Okay. And then there's one key word. And where's that key word? Well, where was it? And they reached the 2nd floor. Oh, here we go. the exams fill out at an even rate. That's important to understand. You see, how can I go from 10 pounds to 6 pounds? There's lots of ways to do it. You could just imagine just grab 4 pounds and dump right at the very start and walk up. Or you could say, well, 6 pounds, maybe I get all the way until I just barely get to the second floor, and then all of a sudden I drop the weight there. But evenly says we think of it as constantly going out at always the same rate, which means that if we think of the weight of what's being carried, it's going to change like a flat line. So this is a line. All right, good. Now we're almost there. So this, we want to figure out what's the equation of this line. So what's the force for any value of y? Well, because it's a line, we can figure it out. We say, well, a line is y equals mx plus b, normally speaking. So we need to know the intercept. Well, we have it. It's 10. Okay, so something plus 10. We need to know the slope. Well, we went down by 4 when we went over by 20. So you went from 10 to 6, so that's down by 4, and over by 20, so 4 over 20, negative. So that's, we're at negative 4 over 20 right now, negative 4 over 20y plus 10, which means we really have negative 1/5 y plus 10. So that says if you give us a height, this is how much the exams currently weigh at that height. And you can check. All right, plug in height 0, which means we're at the bottom. You get 10. Plug in height 20. Well, you'll get negative 4 plus 10, which is 6. Good, good. All right, it's good to check, right? So now we're ready. We have our force. That's really the hard part. The last thing to do is add it up. So we're saying our work is the integral. We start and stop at 0 and 20. So integral means we're adding up. Our force, which is negative 1/5 y plus 10. And then the little tiny distance as we move, which is dy. Force times distance. Well, this is pretty straightforward. So this turns out to be integral of negative 1/5 y would be minus 1/10 y squared. And of course you have to add 10 times y. Evaluate from 0 to 20. And now, it's nice to have a 0. 0 says easy to evaluate. Woohoo! Plug in 20. 20 squared, well, 20 squared is 400. Times by a tenth would give us 40. So then it's negative 40, and then plus 20 times 10 is 200. So we end up with 160. Now it says to include units. So what are our units? Well, our y is measured in feet, and this is measured in pounds. So 160 foot-pounds. And there we go. There's our answer. Now, by the way, now that you see what we're doing, we can say, look, it's really equivalent to saying, if we can sketch our force function, it's the same as saying, what's the area here? So if you have a way to find this area, then you found the work. And of course, this is a pretty easy shape to find the area for. One of the things you can do is if you were to imagine going to the halfway point, you could do the following. You could take this little triangle and flip it over and fill in that space exactly. And so then you'd have a rectangle. Height would be halfway between 6 and 10, which is 8. The width at the bottom is 20. 20 times 8, 160. So that's another way you could see the answer. But good. We're making progress. Okay, well, let's do another problem. So, a 50-pound bucket will be raised from ground level to a height of 10 feet. Now the bucket is attached by a heavy chain, and it's so heavy it actually has weight that we have to pay attention to, weighing 1 pound per foot, to a pulley 20 feet off the ground. How much work will it take to lift the bucket? So let's see if we can get a picture going here. We have the ground. There we go. We have our bucket. So here's our bucket. All right. And there's a heavy chain. So there's this chain. And keep in mind, it goes up to a pulley up here. So here's our pulley. All right. So there we go. Now we have our rough picture. We'll mark some heights here. When we start marking things like heights, we should really talk about coordinates. Again, we have to pick. Now, we want to pick things which make sense. Think about the picture. So here, what makes sense? Let's put ground level at 0. And our pulley is up here at 20. Okay. So now we say, all right, there's our basic picture. And of course, we are doing what? Well, we're moving it not all the way up. We're just moving it up to height 10. So you have to think about, well, what's happening when we're part way up? So when we're part way up, what's happening is our picture looks something like that. So what's contributing to the weight? Well, there's two things. There's the bucket and there's the chain. So if I'm at some height y, so here's my height y, how much do things weigh? So we have two things, and so we'll just break our weight into two parts. So our weight, which we think of as our force, at some height y, is the bucket will always weigh the same. It's always 50 pounds. Okay, no problem. Plus the chain. Now the chain, well, we know it weighs 1 pound per foot. And so the question is, well, how many feet of chain do we have to pay attention to? And it depends on how far up we've moved. As we move our bucket up, the chain is wrapping around. See, the chain that's being wrapped around the pulley, we don't have to worry about that anymore. It's not contributing to the weight. It's no longer part of the equation. So it's just the chain from the pulley down to where the bucket is. So what we need to pay attention to is this quantity here. So that would be 20 minus y. That's the length of the chain. So then we times it by 1. So if we think about this, this is the number of feet of chain. That's what the 20 minus y is. And here, what we have is the number of pounds per foot. So you see when we multiply them together, we get number of pounds. Because that's what our force should be at the end. It should be something that's a measurement of force, which is usually pounds is what we tend to use. And then we have here our bucket. So it's our bucket plus our chain combined together becomes 70 minus y. So that's the weight. Now, where do we start and stop? Well, we need to start, we're at ground level, and go to 10. So 0 up to 10. So here we go. So our work will be the integral 0 up to 10 of 70 minus y dy. Our force, distance. So that becomes 70y minus a half y squared. And evaluate from 0 to 10. And this becomes 700 minus 1/2 times 100. Well, half times 100, that's 50. And so we end up with 700 minus 50 is 650 foot-pounds. And there we go. Now, of course, one of the things you should always ask is, does the answer seem reasonable? Now, we should expect a positive answer if we've set things up correctly. If we have a negative, there's probably an issue with our setup. But some things we can ask are very simple, like, well, what should be true? It should certainly be at least the amount of work if we just lifted that bucket by itself. So the bucket weighs 50 pounds. You move it 10 feet. 50 times 10 is 500. So it better be at least 500. It should be more than that because of the chain. So 650 is more than 500. but it's not something like ridiculously more. It's reasonable. If we had seen an answer like, well, it's going to be like a million foot-pounds, that would make us say, whoa, hold on, a million is kind of high. Yeah, there's work, but not that much work. It's not the world's largest bucket. So one of the things that's good to get into is the habit of saying, hey, is my answer coming out reasonable? And if it's not, check your setup and check your computations, because it's easy to see that, well, hey, maybe there was a mistake that was being made. All right, good. Well, let's try another problem. So, given that it takes 4 units of work to stretch a spring 1 foot. So we have a spring, and we said, if I want to stretch it just 1 foot, that's 4 units of work. Now, I'm going to stretch, and I'm going to be willing to use 9 units of work, 2.5 times as much work. How far will the spring, how far will it stretch? Well, if I'm putting in 2.5 times as much work, it feels like I should get 2.5 times as much length, right? Except the farther you stretch that spring out, the more the spring sort of resists and says, you have to put in more effort as I stretch out farther, because I'm going to start trying to pull back against you more. So we have to take that into account. So I don't think we're going to get 2.5 feet. How many will we get? Well, we need to figure this out. Now, the basic thing is whenever we see a spring, we think of Hooke's law. So Hooke's law says that the force, and oftentimes it's written this way, force is some multiple times x. Well, what does that mean? Well, what you have is you have a spring, and naturally a spring has a certain length. So if you said, look, if nothing was acting on it, the spring would be yay long. Then you start to pull on it. And so if you have a force attached to it, well, it might elongate. And so now, here's our force, and the change in the distance, this is what we're calling x. So the force is proportional to how far you've stretched the spring. Now, why do we have the k? Well, the k has to be there because you have different types of springs. You might have a slinky, which is super easy to stretch, or you might imagine you have some springs from some old vehicles that they use for shocks, where they're like industrial strength, and they're monster sized, and it's just like those things are not going to be pulled easily. They are designed to have a larger value for k. Okay. So let's think about it. What don't we know right now? Well, we actually don't know what is k, because that depends on the situation. So let's work on figuring out k, because it did give us some information. We're told it was 4 units of work to stretch a spring 1 foot. So let's go through the computation. So the work to stretch it 1 foot would be, if we add it up from 0 to 1, so we natural resting state down to 1 foot of the force. And we'll just do it in a very general statement here. Okay, so that's integral 0 to 1 of k times x. Well, that's not so bad. That's going to be 1/2 k x squared. See the 1/2, because when you integrate x, you get 1/2 x squared. And you evaluate 0 to 1. So, easy, 1/2 k. But remember, that's our work, which we said is 4. So 4 is 1/2 k. So I say, aha, this tells us that k is 8. So now we can update and say this is our real formula for force. Our force is really 8x. So now that we have that, we say, all right, we're going to use 9 units of work. So what are we doing? Well, we know our work is going to be 9, and that's going to be the integral from 0 to however far we are able to get. So that's what we don't know. We don't know the bounds. That's okay. If we did, there wouldn't be any problem. And we like to have something to solve. And then we're going to do 8x and dx. Force dx. Well, that becomes integrate. If you integrate 8x, you get 4x squared from 0 up to b, which becomes 4b squared. Nice thing is, you plug in 0, you get 0. So rearranging, we can say, aha, b squared is 9/4, or we can say b, take the square root of that, is 3/2. 3/2 what? Well, 3/2 feet. And there you go. So even though we more than doubled the amount of work, we got only about 50% longer. So it just goes to show you, it really becomes a lot harder to stretch that spring the further it goes along. And it agrees with our intuition, which is good. Things should work intuitively. It's nice to develop that good intuition and problem solving, right? Okay, on to the next one. A storage tank has the shape of a cone, which is 6 feet across at the base and 6 feet high. All right, well, let's see if we can get a good idea of what we're talking about. So a cone tends to look something like this. And here we go. So there's our tank. Kind of a weird shape for a tank, but that's certainly okay. Tanks can be any shape they want. We don't make any judgments. We're not here to judge. And we're told it's 6 feet across at the base. So this is 6 feet. And the height is also 6 feet. So there's 6 feet as well. All right. The tank is currently full of a liquid with a density of 50 pounds per cubic foot. So it's completely full of some liquid. So, all right. Yeah. There we go. It's all full. And what do we want? It's being emptied by being pumped out to a point 4 feet above the tip of the cone. Well, okay, so we need to get it to some point here. So this is 4 feet. So we're moving, essentially, what's happening, if you like, is we're going to pump it all the way out to that level. So maybe from here, we don't know where it's going after that point. We just need to get it to that point. All right, so there we go. We're emptying this tank. We know the size of it. We know how much the water weighs. We have the density. We have the ability. We know where it's going to. So then the question, what's the total amount of work done by emptying the tank? Okay, so we need to remember our basic setup. So when we talk about anything that involves pumping, or if you like emptying, if you have to empty something, the way we do it is to say the following. Our work is adding up from where we start emptying to where we stop emptying. So this is the part that's being emptied. We don't always have to empty the whole thing. We may just empty out a part of it. So we're doing what? Well, we're going to have our distance, which is how far we have to move our little piece. The density, how much does that, what's the weight of that piece, the density of that piece? Well, it's part of the weight, right? Because we have to multiply the density by the volume, which we further break up as an area and as a thickness. Okay, so there we go. That's our basic formula. We have to figure out what's happening to each one of these pieces. There's 4 pieces, but actually the thickness is super easy. Because what does the thickness represent? Well, the thickness, if we think about it, the slice is doing something like this. So here's our slice, and so our thickness will usually almost be dy. Because we like to think of things vertical in terms of y. We need to decide what are our coordinate systems. Where does y go? Now, we could put 0 in lots of places. We could put 0 here at the very bottom. We could put 0 here at the tip. We could put 0 to where we're pumping it. We could put it anywhere we want. Now, you might say, where do you put 0? In some sense, there is no wrong answer because each one of them will help us solve. So if there's no wrong answer, is there at least a good answer? And generally speaking, yes, there tend to be 2 good answers. And if there are triangles involved, try to put 0 where you see the vertex, the tip of the triangle. If there are spheres involved, try to put 0 near the center of the sphere or at the center of the sphere. Okay, so if you see triangles, use the vertex of the triangle. If you see circles, spheres, use the center. Now you might say, well, wait, there's no triangle. It's a cone. But if you can imagine, if you slice the cone, lo and behold, a cross-section looks like a triangle. So it really is a triangle. So we're going to put 0 at the very top of the triangle. So here we go. This is going to be y equals 0. Now, there's 2 decisions to make. Where is 0 and which way is positive? Let's go ahead and make positive going that direction. So that would mean that this part right here is y equals 6. And this part to where we're going to is y equals -4. Now you might say, are we allowed to orient kind of in the opposite of what we might think us normally doing? And the answer is yes, we absolutely positively are. Because we get to pick our description. We get to decide how we describe things. And we can decide in the way that's easiest for us. In fact, that's a good rule of thumb. Make things easy for us. Because after all, we love ourselves. And we want to make sure that we are taking good care of ourselves. All right, so now let's keep making progress in understanding the parts. We should have pointed out, of course, the density is automatic here. It's 50, because we're told. The distance, well, what is that? Well, we're thinking of, here's our slice. It's at some arbitrary y. And when we talk about the distance, it's how far you move that slice up to where you're going to pump it out. Now, in this case, we're not going to the tip of the cone. We're going past it 4 feet up. So we're going to have y, that gets us to the tip of the cone, plus 4 more. Another way to think of it is you're going to take y, subtract -4. Now, always just sort of keep in the back of your mind, distance should be a positive number, and just make sure, is my value going to be positive here? And if it's not, you should reverse everything. So, all right, distance is y plus 4. Bounds are easy. Where are we going? Well, we're going to go from 0 to 6 because that's where our value for y ranges in terms of where that's being pumped out. You might say, wait, do I need to go from 6 to 0? No, you orient according to how you set up your coordinate system, 0 to 6. Okay, so now we have the bounds. That's good for us. What's left? The area. All right, so this one is the one that's going to make us think, well, probably we don't have to be doing too much on this one, because when we look at our slices, we say, hey, when we slice this cone, it's not just any arbitrary shape. What we see are circles. And so we say, okay, so the area, it's going to be pi something squared. If we could just figure out what that something is, life is good. So we're pretty close. We're pretty close. Now remember, I said if you can take a cross section, then we can see that triangle. So let's do our cross sections. Now, why do we love to do cross sections? Well, because triangles are so much easier to work with, and we say, all right, we know some certain things. We have 6 feet across. It's 6 feet in the depth. The height is 6 feet. And now we're saying, well, look, we're going down to a certain level. So here we are. Here's some certain level. And that is at y. So the question is, can we say anything about this length right here? Well, now we can pull out similar triangles. which says, hey, these two triangles, the big one and the small one, are the same angles, so they have the same ratios. So if we compare, for instance, the length across versus the depth in both of them, they have to be the same value. So for the large triangle, length across versus the depth, 6 to 6. It's the same as, we'll call this L, as the length across, which we don't know, is to y, or L equals y. Okay, good. Progress. Now, is that our radius, and why not? You're right, it's not our radius. Good. Well, what's the problem? If you look at it, this is all the way across. For our radius, we only want to go halfway across. So we get that our radius for any depth y is 1/2 y. And we can kind of check. So one of the things you should say is, so let's just sort of check, does it make sense at sort of the ends? So at y equals 0, we should have 0. Perfect. And if we go all the way down to y equals 6, well, we know it's a circle with diameter 6, so it should be radius 3. Aha! 1/2 times 6 is 3. Good. So this is a way to check, all right, is it reasonable at the ends? Does that make sense? And if it doesn't match what the answer should be at the ends, then we definitely made a mistake. We go back and correct ourselves, because it's important to correct ourselves before we wreck ourselves. In other words, it's easier to catch mistakes at the beginning and fix it than to try to catch mistakes at the end. Trying to fix mistakes once you've done all the work, that's annoying. So let's clean this up. So what do we have? Well, we have integral, adding things up, 0 to 6. We have here 50 pi, which is a constant, and there's actually a fourth there, because remember it's a half squared. Well, okay, so I can pull that out. So that's 50 pi over 4. We'll clean that up in a moment. So this is just pulling out the constants. Then you have y squared times y plus 4. So that would become y cubed plus 4y dy. All right. Hey guys, well, I did the problem, and then afterward, somebody was looking at it and said, Steve, you made a mistake. And I was like, wow, that sounds like me. And where was the mistake? Well, you see this y squared? It should multiply by y and by 4. So y squared times y cubed. No problem. But y squared times 4 is 4y squared. Oh, no. Okay, so, whoops. So, yeah, that's wrong. That should be a squared, which means all of that is out. Okay, all right. Well, so let's cover up our mistakes and proceed forward and do it right and see what we get. Well, we can certainly cancel a 2. 25 pi over 2. And we can integrate. So 1/4 y to the 4th plus here 4/3 y to the 3rd from 0 up to 6, which is 25 pi. Let's go ahead, multiply the 2 through. So that's 1/8, because the 2 times a 4th, 6 to the 4th, plus 4/6, 2 times the 3, 6 to the 3. And when we plug in 0, you get 0. Now the nice thing, of course, you see the last term, we can cancel off a single 6, so that makes it a little bit easier. Now here, I can really think of it as, instead of 6 to the 4th, 3 to the 4th, and 2 to the 4th. Now, because 6 is 3 times 2. And 8, that's just a bunch of 2's. So you can actually cancel up almost all the 2's, so you get 2 times 3 to the 4th. Now, 3 to the 4th, well, powers of 3, 3, 9, 27, 81. So 81 times 2 would make this term 162. Here you have 6 squared times 4. Well, that's 36 times 4. It's kind of gross. A little bit of math humor. Gross is 144. So that's what 36 times 4 is. Another way to see that is you can think of this as 4 is 2 squared times 6 squared would give you 12 squared. And okay, that's 144. All right, so 162 plus 144. And that's being multiplied by, in the front, 25 pi. All right, so you can put those together. That would be 306, because you get 200 if you add the hundreds. And 60 and 40 makes another 100. That's why you get to 306. So 25 pi times 306. Now, that's probably about good enough, right? We can say, great, call it a day. Now, if you really, really wanted to, you could push this a little bit further. For instance, you could multiply 3 times 25 would give you what? Well, it'll give you 75. Okay, so 75. And 6 times 25. So when we take 25 times 3, it's really 7,500. And 6 times 25 would be what? Well, it would be 150. Right? 120 plus 30 times pi. And so we could write this as 7,650 pi. And there we go. There. All right. An answer. And now, not only is it correct setup, we did some correct algebra. Woohoo! Twice as correct. All right. Well, good. Let's keep going. And hopefully, we'll try to be more careful. So let's try one other problem. Similar problem. A trough with a triangular end is completely filled with molasses. Oh, that's a bunch of malarkey. No, it's molasses. And it has a density of 100 pounds per cubic feet. That means it's pretty dense. It's very, very thick. The tank's dimensions are shown in the picture below. Ah, that's nice. They gave us a picture. How much work is required to completely empty the tank by pumping all the molasses through a tube extending 2 feet above the top of the tank? So, in some sense, this is not such a bad problem because a lot of it is set up. Now, we do have to make a decision. Where do we put 0? Now, if we go by the philosophy we talked about in the last problem, you should say, well, I see a triangle, put 0 where you see the vertex. That's perfectly fine. It's not the only answer. You can put 0 wherever you want, but I think that's a reasonable answer. So let's put in 0 here, and let's make our increasing, our what we call positive, heading up. So that would say the top would be at 3 because we're completely filled, and we're going to get up to 5. Now, the basic idea whenever we have a pumping problem is to say, let's not pump everything, let's just pump a slice. So we're going to take our little slice here and try to understand how much work does it take for us to pump that little slice. And if we can understand that, then we're good to go. So when it comes to pumping a single slice, of course, you have your distance. Then you have to figure out the force, which is a combination of density, area, and thickness. In other words, it's density times volume, and density times volume gives you weight, and we're adding these all together from wherever we start to wherever we stop. And there we go. See, now we've rewrite it. It's actually pretty easy to remember the basic, what does everything represent? So instead of saying, oh, it's 2 pi, but then there's like this weird thing, it depends on how we label things, distance, and I have to memorize like 20 different formulas. No. Just say, it's a distance. Think about the problem. It's a density. Think about the problem, the area. And now you say, all right, now we adapt. Because we want to be adaptable. That makes us more universal. We can solve more problems. Now, some of these are pretty easy. They're basically free. The density, it's a freebie. That's 100. Our thickness, well, that's our height of our slice, that's our dy. That's another freebie. Our bounds, we just have to think about what's happening. Well, we're told it's completely filled. We start at 0 and go up to 3. So that's good. So 0 up to 3. Our distance is not bad. What do? Well, here we think of our slice is at y, and we ask ourselves the question, how far is it from where we're moving it to? So another way to think about what's happening is like we have this small slice, and we're just going to move the whole slice up, and we're going to do it for every single slice. So we're moving it one slice at a time up until we get it all out. So what's that distance? How far up did we have to move it? Well, it's the difference. So we have to end at 5. We're starting at y. So our distance would be 5 minus y. And you can check that this is something that makes sense. It should be a positive value. Y is going between 0 and 3. And so when we have at the bottom y equals 0, it says we need to move it 5 feet, which agrees. At the top, when we're at 3, we have to move it 2 feet, and that agrees. Think of the picture. Does it make sense in terms of the picture? And if it doesn't, re-examine how you set things up. Really, most of the work in these types of pumping problems, the majority of it comes down to the area. So you'll see we're like, hey, look, we've got these bounds and these other 3 parts done almost automatically. Now we got to spend some time talking about area. So let's talk about area. If we look at our cross sections here in this case, we see, look, these cross sections are kind of nice. They're rectangles. And one length of the rectangle is 10. So our area is going to be something times 10. Okay, so the only thing that's left is, well, what's the dimension of the other side? Now we turn to our triangles. And for this, we're going to be pretty good shape because the triangle is going to look a little familiar if you saw the last problem. What you see is we have something where we have 3 feet up and down. We have 3 feet across, right? Because those are our measurements, 3 and 3. And now we, in addition, are saying, well, we are going to go up to some distance y. And the question is, what's this length across? Well, we call it L. And these triangles are similar. So L is to y, the length across to the depth, as 3 is to 3, length across to the depth, which really tells us L equals y. So that's the length of the other side from similar triangles. Now we have it all put together, and we say, cool, let's do some integration. So let's clean this up. 110 are constants. Pull that out. So that makes it 1,000. And then what? Well, we have the integral, 0 up to 3. And so we've taken care, we've gotten the bounds, we've gotten the 100 and the 10, so it's 5 minus y times y. So that would be 5y minus y squared dy. So we integrate. This is not so bad. So that's 1,000. Then we have 5 halves y squared minus 1/3 y cubed. And evaluate from 0 to 3. Now, one of the nice things is if you can ever get 0 in your problem, you should. Because 0 is a really wonderful number when it comes to evaluation. When you plug in 0, you get 0. Aha! It's fantastic. So try as much as possible. Try to put 0 as one of your bounds if you can. So that's something else to keep in mind. So we really just need to plug in the 3 here. So let's see, what is that going to give us? Well, that's going to be 1,000 out in front. Then we're going to get 5 halves times 9. Well, whatever that is. We'll work on that. And then here we have 1/3 times 3 cubed. Well, we can cancel 1 3. So really, we end up with subtract 9. And now, if you look at this, that actually is starting to look pretty good. because notice we have 9s in common, so you can pull that out. So what do we end up with? Well, if you pull the 9s out, you get 9,000. Then you have 5 halves minus 1, because you pulled the 9 out times 1,000. 5 halves minus 1. Good. Well, 5 halves minus 1, that's 3 halves. So we get 9,000 times 3 halves. Well, 9,000 times 3 is 27,000. We're getting close. So 27,000 over 2. And now, if you take 27,000 and divide it by 2, well, that's going to be 13,500 foot-pounds. There we go. All right, so that's how much work it's going to take for us to empty out our tank. 13,500 foot-pounds. Good, good, progress. Good. Well, let's do one more. Because there's one more type of problem we haven't done yet, so we should do that, and that is the problem of force. Which brings us to our last problem. Woohoo! We've gone to the end. A submerged plate has the form of an upside-down isosceles triangle. So there we go. There's our picture. See, it's upside down. Well, whatever that means, upside down. Now, the base is 4, so we can mark that. We'll put here, this is 4, and the height, 3. Okay. Currently, the plate is submerged so that the top of the plate is 2 feet from the surface of the fluid. All right, so we should probably make a little note here. This is 2 feet. And what else do we have? Given the fluid has a weight density of 64 pounds per cubic foot, find the force on one side of the plate. In some sense, you could say what's happening. Well, it's actually the water pushes from both sides, but you also might say, well, this is a triangular plate, and you might have it on part of a hull of a vessel. And then it's water pushing on one side. In the end, it doesn't really matter. We just have to push it on one side. So this is about force. So how do you find force? Well, you can kind of figure out what's going on. At the end, when you think about the force, we want our final answer here because of our units. It's going to be pounds. And so we should end up with something with pounds. And our basic formula here is we're going to add up the little pieces of force. So we're going to add start to finish. And then we have a depth. The further down you go, the more force you feel. And then what else do you have? Well, you have a density. You have a length. Whoops. Length. There we go. And you have a height. Now, where do all the pieces fit in terms of the picture? Well, density, of course, just hard to draw that in a picture. Depth, well, we're thinking about the following. We're taking a very thin strip, and we do it perpendicular to the vertical direction because we want to have a consistent depth. So the depth is how far down we go. That's the depth. Okay, we understand that. We understand density. The length, how far across from side to side. No problem. And the height, that height is different than depth. See, depth, how far are we from the surface of the water? The height is talking about the little change here. So the change in the y. So this is almost always dy. The only time it's not dy is when we're choosing a symbol other than y. Yeah, we can choose whatever symbol we want. There's nothing sacred about symbols. Symbols can be whatever symbol they want, and we still get the same thing. All right. Well, there are some other things we know as freebies. The density. Okay, that's going to be 64. Good. And now, everything else, the depth, the length, the bounds, we need to have a coordinate system in place before we can talk about them. All right, well, let's make some decisions. Well, what decisions do we have to make? We have to decide where is 0. And where did he put 0? Now, in some sense, I think there are two reasonable candidates for 0 here. And let's talk about them. One reasonable candidate is to put 0 at the surface. So then you say, okay, now we know our depth. It's whatever y is. The other one is to put 0 here because you have a triangle. And then it makes it much easier to work with. Which one is correct? Well, they're both correct. It's not that one is wrong and one is right. It's whichever one we prefer. But let's go through and set up the both of them eventually. Well, we'll pick one for right now. Suppose for a second we put 0 here. There's no reason why we can't. And we put 0 here, and we'll just say we go up is that direction. So that's, when I say up, positive is going to correspond to that direction there. So with this setup, what happens? Well, what happens here is, where do we go? What are our bounds? Our bounds are starting at 0 and going to 3. Okay, 0 to 3. What's our depth? Well, where's the water line at? See, the water line would be up here, 3 feet plus 2 more feet. This would be at 5 feet. So if my slice here is at y, the depth would be 5 minus y. Our density is what it is, it's 64. Our length, now we say, okay, draw the picture, and look, triangles. So when you see triangles, we oftentimes think of similar triangles. So we have a distance is y here versus 3, the bigger one, 4 across versus our length. So what we get is that the length is to y, this length here to that length there, as 4 is to 3. The length across versus the length down. Or we could say the length, look, it's 4/3 y. So that's what goes there. So times that by 4/3 y. All right, that's our pieces. Don't forget the dy. And now everything's set up. So, well, what can we do? Well, we can pull out the constants. 64 times 4, 256. Now, that's because it's powers of 2. It's fun to do powers of 2, right? 2, 4, 8, 16, 32, 64, 128, 256. Then it's like, why not just keep going? 5, 12, 10, 24, 20, 48, 40, 96, 81, 92, 16,384. It's a lot of fun. It's a great, while you're walking around, it's like, well, let me think about my powers of 2. See how far I can get. All right, fun pastime. But here we go. So 256 over 3. That's the constants. Pull them out. Integral. Haven't integrated yet. And then if you distribute the y through, 5y minus y squared dy. Well, that's something we can integrate. So that would be 256 over 3 times, well, 5/2 y squared minus y cubed over 3. Evaluate from 0 to 3. And now, plug in 0, you get something nice. You get 0. Plug in 3, you get something 3. Okay, hold on. What do you actually get when you plug in 3? Well, you're going to get 5/2 times 9. And then 3 cubed is 27 divided by 3 is 9. Well, 9's common, so you can pull it out. So you get 256 times 9 over 3. Then you have 5/2 minus 1. Well, that ends up being 3/2. So we can do a little bit here. We can cancel a 3. And then we can say, well, we can also cancel a 2. So you end up with 128 times 9. Well, that's almost close enough we could do that, right? Because 128 times 9, we could think of it, 100 times 9 is 900. 20 times 9 is 180. 8 times 9 is 72. And so if you add those all together, we'd have a 2, a 5, 1, 1. So 1,152 pounds. And that would be our answer. Okay, so that's if you put 0 down below. What if we didn't put 0 down below? Okay, we got an answer. Let's just talk about the setup. And then hopefully we're going to be like, oh, that makes sense. Okay, remember, we're going to shoot for that oh moment. So let's see if we get there. So suppose, let's do a very different color. I'm going to switch to red instead of this very dark red. Now it's just normal red. Suppose I put 0 here, and I sort of said, let me go down. What changes? Okay, well, where is the plate? Well, the plate starts at 2, and it goes to 5. So I'm going to be adding up from 2 up to 5. What's my depth? Well, my depth is now simply y. Density hasn't changed, still 64. And then there's the length. Well, we'll come and figure that out. So here is where things get a little bit interesting. Where can we put that in? We'll put it on up here. We can squeeze it in. So let's think about what's true. I still want to do that same kind of ratio here that we have. So we still have, of course, the big triangle. That isn't changing. That's 4, and that's 3. This side is L. But now, the real thing that changes, the only thing that changes, is what is that? Well, what it is, if you think about it, you see, going down all the way to 5 would get us to the very tip. So this length right here is 5 minus y. So whatever your choice for y is, that's how far you have to go to get all the way down to the bottom. Think about it this way. I went from the surface down to the current level as y. If I wanted to get all the way down to the tip, which is as at depth 5, I have to go 5 minus y left to get all the way to the bottom. So you get the same kind of setup, except instead of y, you get 5 minus y. So the result is that your length is 4/3 times 5 minus y, and then you have a dy. So what's changed? Well, the pieces which have changed, if we compare the two, so are the bounds, they've changed. The depth, that's changed. And the length, that's changed. So you might say, so pretty much everything has changed, right? Take a close look. How are these two integrals related to each other? Can you see something? They're related to each other by a substitution. What's the substitution? If you make the substitution, let's say capital Y equals 5 minus y, this integral becomes that integral, and vice versa. So what happens is substitution in this setting, if the different coordinate systems, it's just a change, right? So changing coordinates is a substitution change in your integration. So at the end of the day, your integration problem really won't change that much per se. It's just a matter of how clean do we want it to be at the start. Our goal, of course, let's make it clean from the beginning. If it's clean from the beginning, it's greater. So that was our great, oh, different coordinate systems, same integral problem, it's just a change of variables. That's what change of variables accomplishes when you're doing these setup problems in physics. A change of variables is helping you accomplish a change of coordinate system. That's good to know. And the more you know, the better it is. All right, good. Well, a lot more physics problems that we can talk about. So probably should keep doing some more practice, and we'll keep learning more. We'll get really good at this. A lot of it boils down to just learning to set things up. Once you have things set up, you realize, it's beautiful. It's beautiful. By the way, one thing we didn't do, since you waited so long, I just want to point this out really quick, because I'd feel bad if I didn't point this out, is to say, let me make sure I have the right formula in mind. So, because it's easy just to say that I have so many formulas, they all sort of like blend together, and I'm not 100% sure which one is which. You can check to see if you have the right formula in mind if you think about units. Notice what we were asked to find. We're asked to find a force, so the units of what we should be asked to find should be a force. So if you check, you say, well, let me think about what my measurements are. Depth, that's a feet. Density, that's pounds per cubic feet. A length, that's a measurement, that's feet. And height, that's measurement, that's a feet. And if you just check your units, lo and behold, you see that you end up with pounds. And therefore you get the right answer. So that's actually a nice way to make sure, hey, I'm onto something. I'm doing it right. So, wow, all this great stuff. So many things to learn. Okay. Have a great day.